You type a simple thought into an AI chat interface. Tokenization is fascinating, followed by a rocket emoji. To humanize, that input consists of 4 words and 1 symbol, but the model's application programming interface logs an entirely different measurement. It processes exactly 9 units of data. Large language models do not read human words. They parse an invisible, mathematically generated alphabet known as tokens. This diagram illustrates why engineering an AI to read whole words fails. While an English dictionary is a closed system, internet text includes millions of typos, slang, and proper nouns. Assigning a unique identifier to every possible word variation would exhaust the system's storage capacity. The alternative is feeding the AI 1 letter at a time, but breaking sentences into individual characters creates strings of data so long that the processing sequence overwhelms the AI's limited short-term memory window, crashing the model. Building a functional language model requires a mathematical compromise, a system capable of handling any misspelled word or obscure emoji without consuming excessive memory space. The solution comes from a 1994 data compression algorithm called byte pair encoding, or BPE. Looking at this diagram, we can see how byte pair encoding handles our example sentence. The algorithm splits the text based on frequency patterns observed during training, ignoring human grammar rules. The word tokenization is severed in the middle. The letters T-O-K-E-N remain together because they form a common sequence. The letters I-Z-A-T-I-O-N break off as a separate, highly frequent suffix. Non-standard text behaves differently. Because a rocket emoji lacks standard linguistic frequency, the algorithm fractures it into 3 raw, fundamental computer bytes. These varied chunks act as raw material. They are the literal building blocks the AI uses to construct its understanding of the prompt. By prioritizing mathematical frequency over linguistic rules, the algorithm creates an alien alphabet. The boundaries of these specific chunks dictate exactly what the AI is capable of perceiving. As the chunked sentence moves forward into the internal processing pipeline, all trace of human text is permanently discarded. This visual shows the creation of token IDs. The AI maps each color-coded chunk to a permanent, unique integer, drawn from a fixed vocabulary list of roughly 100,000 available slots. The user's prompt about tokenization is now represented entirely by a sterile string of numbers. A neural network cannot deduce meaning from isolated integers. The number 262 and the number 30,642 possess no inherent relationship to each other. These IDs are empty labels. To operate, the AI must perform a mathematical translation, injecting semantic meaning back into the raw data. This translation relies on embeddings, a mathematical process that converts the flat integer IDs into complex, high-dimensional vectors. In this 3D scatter plot, we can see the embedding process. The AI plots these vectors in a vast physical space, placing conceptually similar tokens close together, while pushing unrelated concepts far apart. Because the architecture processes all these plotted tokens simultaneously, it instantaneously loses track of the sentence's original word order. To fix this, the system injects a specific sequence code into each vector. This forces the floating concepts back into a sequential order right before they enter the transformer layers. The AI calculates probabilities along this ordered curve, testing billions of parameters to output a single integer, the most likely next token ID, which is finally decoded back into text. The response appearing on a screen is the direct result of millions of spatial calculations executing exclusively at this token level. This internal mathematics drives physical consequences for global AI capabilities and infrastructure. This diagram maps the tokenization trade-off triangle. Every token generated forces engineers to balance memory allocation, computational cost, and inference speed. An English prompt might cost 5 tokens. The exact same meaning translated into Hindi splinters into 15 tokens, overloading the cost and memory nodes. Because byte pair encoding algorithms are trained primarily on English datasets, they are less efficient at chunking other languages. This burns through user budgets and context limits at up to 3 times the rate. This same chunking mechanism causes common AI hallucinations. When a large language model fails to count the letters in the word strawberry, It is because the model literally cannot see the individual letters, only the rigid, predefined chunks. Tokenization acts as an economic bottleneck, hardwiring specific biases and blind spots directly into the world's most advanced systems. The ultimate engineering challenge is whether computer scientists can build an intelligence without relying on this rigid translator. Current AI research focuses on byte-level models. These systems attempt to operate directly on raw data bytes, eliminating fixed token vocabularies entirely. Despite this research, the computational cost remains high. Every major production language model today remains dependent on tokenization. When you submit a prompt, you never type a token, and the AI never reads a word. Tokenization stands as the mandatory, imperfect mathematical bridge required to translate human thought into machine computation.